Hello everyone, I'm Zahir Afifi bin Shamsul, AA 250103. Today our PPL project is about first order differential equation which involve the first derivative of an unknown function. These equations are important because they help model real-life situation and dynamic system. So this presentation video is proudly presented by our group members Adam bin Hasrul, Muhammad Haziq bin Zaimi, Muhammad Akmaldini bin Mustafa, and I myself, Zahir Afifi bin Shamsul. There are several methods used to solve first-order differential equations such as separable equation, linear differential equation, and exact equation. However, for our project, we only focus on separable equation method. But how can we apply this order in real life? Our group worked on two case studies. The first case study is the Green Horizon Smart City. In this case, we calculate the projected population for the year 2040 based on the population data from 2026 and 5-year trend. This prediction is important to determine whether the new water treatment plant can support future water demand and provide enough water supply for the growing population. Therefore, we also need to calculate the total daily water demand in megaliter per day MLD to ensure whether a supply of 150 liters per person per day is sufficient for the long-term operation of water treatment plant. The second case study is the Jabatan Putra Perdana Pier Pour. In this situation, a massive concrete pour caused the concrete temperature to become extremely high. Using Newton's law of cooling, we calculate the safe time for removing the formwork. This calculation is based on the initial temperature, which is 80 degrees Celsius, surrounding temperature 25 degrees Celsius, and 2 hours of cooling temperature, which is 10 degrees Celsius. This is important to prevent the thermal shock, which can cause cracking and structural failure if the concrete cools too quickly. So I'm going to pass to my friend Muhammad Akmaldini to explain the methodology used.
Thank you, Zahir, for the lovely introduction. Now, my name is Muhammad Akmaldini, and I will continue with methodology. So I will guide you on how to derive both ODE models by using separation of variables method. For the first case, case A growth model, we were given dP over dP is equal to Kp. Now, we need to separate this both equation into its own derivative to solve this equation. We will get 1 over P dP is equal to K dP. We need you to integrate both sides to get ln P is equal to Kt plus C. We will use exponential function to remove the ln function. We will get e to the power of ln P is equal to e to the power of Kt plus C. We can cross out e to the power of ln by using the exponential law. So we will get P is equal to e Kt plus C. Now EC we can equals to A because we will need one constant only. So P is equal to A times e to the power of Kt. So when t is equal to 0, P is equal to P initial, where it is equal to 10,000 based on the table data given. As for our last conclusion, we can conclude that Pp is equal to Po times e to the power of Kp, which is the exponential growth model given for us to find, where Po is initial population and K is our growth constant. For the next case, which is case B cooling model, we were given dP over dP is equal to negative K times T minus Ts. So we need to separate this ODE into its derivative to solve this equation. So we will get 1 over T minus Ts dP is equal to negative K dP. So now we need to integrate both sides to get our answer. We will get ln T minus Ts is equal to negative Kt plus C. Now we have to use exponential function to cross out e to the power of ln. We have e to the power of ln T minus Ts is equal to e to the power of negative Kt plus C. we will have T minus Ts is equal to e to the power of negative kp and times e to the power of c, where e to the power of c, we can use it as one constant, which is To minus Ts. When we substitute t is equal to 0 into our equation, we will get Ts plus To minus Ts is times with e to the power of negative k times 0. So for our last conclusion for the final equation, we can conclude that Tt is equal to Ts plus To minus Ts is times with e to the power of negative kp, where this is the exponential cooling model given in the equation for us to find. So that's all for the methodology, and we will continue with our manual solution by Adam. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adam bin Zazul. So today I am going to talk about mathematical derivation for our discussion today. So looking at here, we have the model derivation, which has already been explained by my group member Akmal Dini just now. So I am showing this just to heads up for us, so we could keep in mind what are we going to do and what are we going to solve. Alright, so moving on to this next part, which are case A. For us, we are the group 1 and we have been given an initial population P0 equals to 10,000 and population after 5 years are 12,500. So for this part, we work as a team, find the calculation manually, but then later verified using Excel calculation by Haziq, my group member. So knowing that P0 equals to 10,000 and P5 are equals to 12,500, we can substitute this amount into our model. So we ends up with 12,500 equals to 10,000 exponent to the power 5k. After substituting, we can start finding our k, which are crucial for this case. So looking at here, 1.25 are equals to exponent to the power of 5k, and then taking the natural logarithm, ln 1.25 are equals to 5k and ends up with k are equal to 0.04462. So after getting our k, we can go on to the first problem, which are forecast of population in 2040. The year 2040 corresponds to t equals to 14. Substituting into the model, we end up with t14 equals to 10,000 exponent to the power 0.04462 times 14, as t are equals to 14. So after substituting, we end up with t14 equals to 18,680. This means that the projected population in 2040 is approximately 18,680 people. With that in mind, we can go on to our second problem, which are the daily water demand, megaliters per day. The daily water demand is calculated using 1 megaliters equal to 1 million liters. So with that in mind, we end up with a formula of MLD equals to P times 150 divided by 1 million. So substituting the earlier amount, it ends up with 2.802 megaliters per day. Therefore, the estimated daily water demand is 2.80 megaliters per day for the case A. And for last but not least, we are going to work on our case B. So just like earlier, the concepts are pretty much the same, but this is the temperature problem. So the temperature variation follows the Newton's law of cooling. So for the Newton's law of cooling, the function T equals to Ts plus bracket T0 minus Ts bracket exponent to the power negative KT. T0 are initial temperature, Ts are surrounding temperature. So for T0 and Ts, P as a group 1 has already been given the amount, which are T0 equals to 18 Celsius and Ts are 25 Celsius. So in the problem, it is stated that after 2 hours, the temperature drops by 10 Celsius. This means that the temperature starting from 80 for us drops to after 2 hours drops by 10, means 18 minus 10, which are equals to 70. So T2 are equals to 70 Celsius. So with this in mind, we can substitute this this amount into the earlier formula. So after substituting, we ends up with 70 equals to 25 plus bracket 18 minus 25 bracket exponent to the power of negative 2k. Just like earlier, after substituting, we put on the natural logarithm and find the k of 0.1003. So just like earlier, after having the k, we can move on to our first problem. So our first problem, it is that time to reach 35 Celsius safety limit. So substituting t equals to 35 Celsius, 35 are equal to 25 plus 55 exponent to the power negative 0.003 t. So after substituting, we can go on put on the natural logarithm and ends up with t equals to 60.99 or roughly equals to 17 hours. With that in mind, we can move on to the second problem. So for the second problem, conversion to clock time. These ones are pretty simple. Basically, the concrete pouring started at 8 AM as it was stated in the problem. Therefore, 8 AM plus 17 hours is the safety time limit. We ends up with 1 AM, which are on the next day. So this means that the safe time for formwork removal is 1 AM on the following day. And that's wrapped it all up. That is all from me for this part. So we are going to go on to the next part, which are the Excel calculation by Haziq. Thank you.
Thank you, Adam. Now, I will demonstrate our digital simulation for case A and case B. For case A, we are required to create a 14-year projection table of population growth. This projection begins in the year 2026 and tracks the data through 2014. To visualize this, we have generated a smooth line scatter plot which highlights the specific growth curve for these cases. We were also given P0 at 10,000 and P5 at 12,500. To demonstrate our digital master, I will show you how this file is fully dynamic. Notice what happened when I changed the value of P0 to 20,000. As you can see, the value of K, population count in our projection table, and the growth curve in our scatter plot update immediately. This proves that our engineering calculation remain accurate even when there are changes in value.
Next, we also created a dynamic projection table where by simply changing the forecast year in the single input cell, the model automatically pulls the corresponding data for both population and daily demand water. To prove how responsive this is, watch what happened when I put in the different target years. First, 2050. Next, mid-range target like 2038. And finally, given a distant projection for 2070. As you can see, the population and water demand update instantly the moment the year is changed. This demonstrates the effectiveness of our dynamic projection table.
Now let's move on to case B. For this simulation, we were required to create a detailed timeline using 0.5 hour increment, extending to a total of at least 25 hours, and a scattered smooth line chart to project the corresponding temperature for every hour. To make this data more intuitive for safety monitoring, we implemented conditional formatting. We have defined a safe zone as any temperature less than or equal to 35 degrees Celsius. You'll notice that as the timeline progresses, the cell automatically highlight in green once the cooling reaches that 35-degree threshold. To show the dynamic nature of this specific case, watch what happens if I adjust the initial temperature to 90 degrees Celsius. As the cooling curve shifts, the safe zone green highlight moves automatically up the timeline. This ensures that the operator can instantly identify exactly when the system reaches a safe state without manual calculation. Now I'll pass to Dini for conclusion.
Thank you so much, Haziq, for the verification using the Excel results. Now we will moving on to our next part of discussion and conclusion, where our final decisions are made. So, the source outlined a strategic shift required to accommodate a growing population, emphasizing that infrastructure must be proactive rather than creative. So, by the year of 2040, the population is expected to reach 18,680 people. This isn't just a number, it represents a specific resource requirement of 2.8 million liters per day of water needed. So, infrastructure requirements need to meet these demands. Local authorities are advised to focus on two key points, which is treatment capacity, which ensuring the facility that clean and process water can be handled in the large volume. Next, distribution system, where improving the network of pipes and pumps to deliver the water efficiently to an exponentially expanding urban population. So, instead of just finding more water, the source suggests managing how much is used. This includes water conservation campaigns to change public behavior and leakage control to fix existing infrastructure, ensuring the system remains sustainable. The source provides a technical breakdown of how temperature management directly impacts the structural life of a building. Now, the thermal safety mechanism identifies a critical period point for concrete to be safe for formwork removal. It must drop to a maximum temperature of 35 degrees Celsius. So based on our 17-hour calculation, if casting begins at 8 a.m., workers should wait until 1 a.m. the following morning before removing the forms. So, removing formwork too early subjects the concrete to thermal shock. This sudden temperature change causes internal fissures where it can cause cracks. While this might not be visible immediately, they significantly shorten the structural life of the concrete. To mitigate this risk, the source recommends moving away from guesswork and using two methods, which is real-time monitoring. So, which utilizing thermometers or sensors placed within the location to confirm cooling is actually occurring as expected. And the second is dual verification. Construction teams must confirm that both strength and temperature requirements are met before stripping formwork. This ensures that the concrete is not only hard enough, but also thermally stable enough for long-term performance. So that's all for me for our final decision. Now we will continue to part A, which is impact on city resources, which is water or sewage. Thank you.